Hello dear students, this is Jayant Mane from Phenolics Academy, Ratnagiri, and welcome to 6th lecture of electrical drives. Today we are going to see the equivalent values of drive parameters. In the last lecture we have seen the fundamental torque equation of motor load system, wherein the equation was T minus TL, means motor torque minus load torque, equals to 0 if the drive is running in steady state. So as both torques are equal, there will not be any acceleration or deceleration. Whatever is the speed by which the motor is running, it will be maintained. But in case there is difference between motor and load torques, then T minus TL will be equal to J d omega m by dt. Whereas J d omega m by dt, this term could be positive or negative. This term is called as dynamic torque. This torque is obviously present during transient operations, means acceleration or deceleration, starting or stopping, speed change of the drive. So this was the simplest equation by which we can represent motor and load systems, but there could be multiple loads connected to the motor. Some loads, so as seen in this figure diagram, first we'll consider loads with only rotational motion. So there are two loads here, load 0, load 1. Load 0 is directly coupled to the motor shaft. So J0 is the inertia of this combined system, and omega m is the speed by which this motor shaft is running. Then this is gear, so n is tooth ratio of one gear and n1 is tooth ratio of another gear. Then this is the direction of rotation and speed of the load, another load. So this another load is having load torque TL1 and inertia J1. So this is the system. So here one load is directly coupled to the motor and another load is coupled through gears. So even this system also should be presented by that simple equation T minus TL equals to J d omega m by dt. So in that case we have to use transformation. We have to convert all these things to the motor shaft equivalent. We have to calculate equivalent values at motor shaft, and then it will be easy to represent this whole system by that simple motor load equation. Now let's see. Let's see, the gear tooth ratio is alpha, this is not alpha, this is actually small a. So let's say gear tooth ratio is small a. So tooth ratio is just like the turns ratio of the transformer or voltage ratio of the transformer. So it is n by n1, and therefore it is also a ratio of the speeds, omega m by m, omega m1 by omega m. As we are also multiple ratio, having multiple ratios or ratios of multiple quantities in transformer case, means if the transformation ratio is defined as n2 by n1, it could be also v2 by v1, e2 by e1, or I1 by I2. So just like this, it could be ratio of the number of teeths or speeds, and like that. So small a is the ratio, transformation ratio of this gear. Then the equivalent inertia or the kinetic energy of the equivalent inertia. This J will be the equivalent total inertia of the motor load system referred to the motor shaft. So obviously the kinetic energy in that whole system is given by half J omega m square. So this kinetic energy must be addition of the individual kinetic energies. So kinetic energy of the load which is directly coupled to the motor shaft and kinetic energy of the load coupled through gear. Therefore the equation is half J omega m square equals half J0 omega m square plus half J1 omega m1 square. Now just we have to remove this omega m quantity, therefore replacing omega m1 in terms of omega m and a. So as there is a square of this quantity, we get a square here. So the equivalent inertia J will be equal to just J0 plus a1 square into J1. So if we know the gear to the ratio, then easily the inertia can be transformed to the motor shaft. So this is how equivalent inertia can be calculated. Similarly, equivalent load torque can be calculated by this equation. So TL equal to TL0 plus E1 square TL1 by eta 1, where eta 1 is efficiency of the gear. So in this way the torque also can be transformed onto the motor shaft. So this is the equivalent load torque. So this is for rotational loads. These two equations are important. Similarly, now there is loads with translational motion. So there could be load with translation motion. Yes. So again, there is motor load, means motor and load which is directly coupled on the same shaft, and then this is the load with linear motion. V1 is velocity, m1 is the mass of the load having translational motion, and this is a converter. It is converting rotational motion into translational motion. Now how this system could be, you might have seen old railway engines wherein the railway wheel is like this. So it is a steam engine. So steam engine is having a piston which moves to and fro. Now if I connect some hinge here and a shaft which is generally called as crankshaft, and if I hinge that crankshaft here at the wheel, and if there is a shaft, in that case when this piston is moving with linear motion, obviously there should be some guide. So into that guide or cylinder the piston is moving, and when it is moving, due to the steam is passed on this side and then on this side, like that. So when it is moving to and fro, this point is moving like this, and due to that this wheel rotates. So this is what linear to rotational motion. Or if I rotate the wheel using some motor, in that case this piston moves to and fro. So this is called as rotational to linear motion conversion. So this is how it is done. So this part is that one. Okay, now we will move on to calculations, how we can calculate the inertia. Again it is a kinetic energy equation. So this is equivalent inertia J, the net speed of the motor shaft. Then this is inertia of the load which is directly coupled to the motor shaft. motor shaft speed, so half J omega m square, like that. And here the kinetic energy is half m1 v1 square. Again, here we cannot eliminate any you can say any quantity, so just rearranging the terms and just writing the equation. J equals, so J equals to J0 plus m1 into bracket v1 by omega m bracket square. So this is equivalent inertia when there is a translation motion load connected to the motor. And now the torque equation. Torque equation is TL equal to TL0 plus F1N1 into bracket V1 omega m. So this is V1 omega m. So this is how we can calculate inertia and torque referred to motor shaft. Now in case there are both type of loads, rotational load as well as a translational motion load, in that case suppose you want to calculate equivalent inertia. Okay, so it could be J plus, okay, suppose there is one load directly coupled and another load connected through this rotational to linear motion converter, and another load is coupled through gears. So in that case we can just add this term, to that equation above. So to this equation number 1, okay, just add here plus that equation, that's part of the equation. So that becomes a system having one load directly coupled to the motor, another load through gear, and another load through rotational to linear motion transmission. Similarly, the term of torque can be added here and you can calculate the equivalent torque. So as simple as that. So I hope you understood this one, how to calculate effective inertia and effective load at the motor shaft.